truth tables, which is a continuation of our previous lectures. And in our previous lectures, we discussed logic gates. And today, I will go over those logic gates discussed in our previous lectures. So, of course, as presented in the previous lectures, we categorize the various logic gates into three, starting with the basic gates, which include the NOT gate, the AND, and the OR gate. So the other category of the logic gates includes, which we consider to be our universal gates. We have NAND, the NAND gate, and the NOR gate. Also, we have special gates, which we also consider to be other gates. Includes exclusive OR and exclusive NOR gates. So these are the various gates that we use when we want to design any digital circuit. So these logic gates, you can design whatever digital circuit you want to design. So now let's see those various gates and how they can be represented in a truth table. So, but for these lectures, I will still draw the various gates, here starting with the basic gates, through the universal, and to the special gates. So now let's start. Of course, if you missed the first lectures, you have to take note of the various gates I will be drawing here. But of course, what you also have to remember is for every input, we are expecting, for every gate by the way, we are expecting to have one or more inputs and basically a single output. But for every input is in one of the two binary conditions. That is, it can be in a very high condition, high state, which is 1, or in the very low state, which you can say 0. That is for every input. So considering A to be an input as our first input, A may be in one of these conditions. The input A may be in one of these conditions. May be in a very high condition or high state, which is 1, or in the very low state, which is what? 0. So now, we are going to draw, understanding this concept that for every input, it must be in one of these binary conditions, the zeros. It can either be in the 0 state or in a 1 state. Okay, so let's start with the first gate, which is we are started with the NOT gate. Or before going to the NOT gate, let's first look at the NAND gate, the AND gate, sorry. Let's look at the AND gate. We have the AND gate, for example. So of course the AND gate, we are expecting the AND gate to have 2 inputs. So input 1 is A, and the second input will be B. So having these 2 inputs, now we are going to draw our gate. So our logic gate is drawn this way. So by the way, we are expecting our output to be Y. So Y is our output. So we have AND here. Oh, this is our AND gate. So basically we have 2 inputs here. We have input A and input B. But since we are expecting for every input here, we are expecting it to be in one of the 2 binary conditions. That is, if input A is expected to be either in the 1 state or the 0 state, and we are also expecting input B to be in the 1 or a 0 state. So by the way, we are expecting to have 4 binaries. So that is 2 for input A, and you have 2 for input B. These are our binaries for the 2 inputs. But let's see what will be the expected output for this for the input passing through the AND gate. But since the operation here is also very key, the AND operation is telling us to multiply the 2 inputs, that is input A and input B. So if we are multiplying, we say Y is equal to A dot B, and the dot is implying that we multiply A by B. So by the way, our output, our final output, when well simplified, will be AB. So this is what we have as output, Y. So if we are drawing our truth table, we should take note of these conditions. And the 0 condition for A, and the 1 and the 0 condition for B. So by the way, you have 4 separate conditions, and which we expect A to be in one of these and B also to be in one of these conditions. So that is to say, if you have an output, you have to check when drawing your truth table. You have to know how many inputs you have. So that input will, the number of that input, for example, you have 2 inputs, that is A and B, and we are expecting each of these to be in one of the 2 conditions. 2. So now to get the outcome, the expected outcome for the 2 inputs, we say 2 raised to the power n. Let's say 2 raised to the power n. So this one, the 2 is our base value, and the n is saying the number of inputs. So in this case we have two inputs. So by the way, we'll be having 2 raised to the power 2. And 2 raised to the power 2 is like, if we are expressing it now, we have 2 times 2. And 2 by 2 is 4, which is the same thing we have here, 2, and we have here 2. So when you add these two, you have 4 here. So we are going to use this 2 for outcome for the 2 inputs to prepare our truth table. But now let's draw our truth table. Of course, we already know our output. So the truth table, we say the truth table let me just arrange it properly. Let's say we say truth table. This is our truth table. So drawing our truth table, we are expecting input A and input B. We have input A and we have input B. And also we have Y to be our output. And our Y is equal to AB. That is what we have. So now for the first input, we are expecting the first condition to be, it to be in a very low state, too low, and a too high state, and we have 1 low, 1 high, low, and high. So having this, what will be our output? So now the easiest way to do this is to still maintain the operation that is being performed, that we know to be performed here. So multiplying these two outcomes, expected outcomes for the input. So 0 by 0 is 0. 0 times 0 is 0. So 0 times 1 is 0. And we have 1 times 0 is 0. And we have 1 times 1 is 1. So this will be our output for 2 input passing through the AND gate. And remember, to summarize this concept here, you can say the output will only be in a very high state if both the input is in a very high state. Otherwise, it is in a low state. Now you can see it is in the low state here. The first input low state, second low state, you get an output in the low state. First in the low state and second one in the low state. You have in the low state a very low state, and you have this one high state, low state, and in the low state, and you have here high, high. So it is, the output will only be in a very high state when the 2 inputs are in the same very high state. So this is the truth table for the AND gate. So let's also look at the second gate. We say our OR gate. We say the OR gate. Of course, we are just going to take off this and get rid of all this now, and also this inscription we have. And let me just take everything because we need to draw our OR gate. So in drawing our OR gate, we have, assuming we have input A and input B, of course the diagram is different. Here is a curve, and then we have this, and you have the output Y, and we say OR, our OR gate. So the output Y will be equal to, the operation performed here is addition, so we are adding input A and input B. So this is our output. So since we have two inputs, there is 2 raised to the power 2, and which is 4. The third one, the 3 basic gates, or the final one, we are looking at the NOT gate. So we say NOT gate. Of course, NOT gate takes one input. That input can also be an expression, but let's first look at it as a single letter, like we take A. So to draw the NOT gate, of course we have this, and so our output is Y also. But remember, the expected outcome for this is 2, and how many inputs you have is 1. So now 2 raised to the power 1 is 2 by 1, so we have 2. But now we know that when an input passes through the NOT gate, it negates or take the complement of that input. So that is Y is now equal to A bar. So taking the complement of A. So that is what we have. So but what's the truth table for this? How can we draw the truth table for this? So we say truth table we have the input A, and of course we have the output Y, which is equal to Y bar. But we are expecting 2 outcomes, just 0 and 1. So we have 0 here, and we also have 1 here. So now we are taking writing the opposite for the outcome showing here. Like we have 0 here as the first outcome. If it is not 0, it is 1. And if it is not 1, it is 0. So we are expecting one of these conditions. So this is how to write or to draw the truth table for the NOT gate. But let us look at, let's see how we can draw the truth table for the universal gates. Of course, looking at the universal gates, we have the NOR gate and the NAND gate. So we say the NAND gate. So for our NAND gate, we can draw our NAND gate as, like, let's still maintain the 2 inputs, input A and input B. So we have first the AND gate, and we invert using the inverter. We invert the NAND gate, the AND gate, so that we have the NAND gate. So of course we still retain Y to be our output. So now, having the output for the AND gate, we also invert, or we take the complement of that output. But let's see how the expression goes. But remember, we are still going to perform the operation, the normal operation for the AND gate. So meaning we are going to multiply the two inputs, like having Y here, which is A, B. So we have Y is equals to AB. But because of this inverter, we are taking the complement of that output. So you have AB bar. So with this, let's see how we can draw our truth table. But let us also remember that we have two inputs. But of course, I expected the outcome is 2. And because of the two inputs, is 2 and 2 by 2. And this one will give us 4. So our outcome, expected one, is 4. So we are drawing, we say truth table. We say truth table. Truth table for the NAND gate. So we say A for the first input, and we have B for the second input. But multiplying A and B, when A and B passes through the AND gate, we have AB. So when inverted, we have AB all bar. So that is what we'll have. Of course, this will provide and this one is NAND. So now let's have we have 0, 0, we have 1, 1, we have 0, 1, 0, 1. So it is very simple. If you can remember that having for the AND gate, the output will only be 1 when both the inputs is 1. Otherwise, they are all zeros. So now for the first and the second, the first and the second input is just 0, 0, 0, and here is 0, and this one is 1. So it is 0. Here is 1, and here is 0. It is 0, and here you have 1. So now we are taking the complement, or we are inverting or taking the complement of this. So if it is not 0, it is 1. If it is not 0, sorry, we have 1, 1, 1, and 0. So we can just say inverting this, we have this as our output. So this is the truth table for our NAND gate. So let's look at the NOR gate. So for the NOR gate, we are going to also perform the OR, and we invert that output. So we say OR gate. So for our OR gate, sorry, NOR gate. So we still maintain the two inputs A and input B. So when the two input passes through the NOR gate, so we have an inverter here, and we have our output Y. So now, since we are adding the two inputs, like having A, it is A plus B. But because of that inverter, we have A plus B all bar. So this one is the NOR. This one is the OR. So not all will give you this. So now having this, let's see how we can draw our truth table. So in drawing our truth table, we say truth table. So of course we have our first input. We have input A, input B, we have A plus B for all, and we have A plus B all bar. So this is what we have. So now with this, you have output 0, 0, 1, 1, outcomes, expected ones. We have 0, 1, we have 0, 1. Of course we know it will only be low in a very low state when the two inputs are in a very low state. Otherwise, they are all in the high state. So this one is 0, 1, 1, 1. So taking the complement of this is just the opposite. So like having 1, 0, 0, 0. So this is the truth table for our NOR gate. So now let's go to our special gates. So our special gate starts with the exclusive OR would be having these two inputs. So now we are going to the exclusive OR gate. So but maintaining the two inputs, input A and input B, having these two inputs, let's try to draw our gate. So this is the gate for exclusive OR. So if our output is equal to Y, so let's see what we'll have. So Y may now be equal to A plus B, and we circle the operator, the plus sign. So how can we draw? What's the truth table for the exclusive OR gate? So now we say truth table we have the inputs. Let's say input A and input B, and we have exclusive OR, the output, our output. So let's say the expected outcome, we have 0, 0, 1, 1, and we have 0, 1, 0, 1. So our output here, for us to get the output for exclusive OR, we have to understand that for the outputs here, we only have an output in a very high state, or let's say in a very low state, when both the inputs are the same. I mean, if input A is in a very low state, which is 0, and input B is also 0, and you have input A as 1, and input B also as 1, so those outputs or expected outcome for the two inputs will always be low. So 0, 0, since we have 0 here and we have 0 here, it is 0. And we have 0 here, but there is 1 here, so it is 1. So we have 0 here, 1 here, and 0, we say 1. And here we have 1, and there is 1 here also, we say 0. So it is saying it will only be on when one of the inputs is on. Let's say one input is on and the other one is off. But when we have the inputs, the both inputs to be in the same condition, like either 0 or 1, we say the output will be 0. So this is the truth table for the exclusive OR gate, for the exclusive OR. So let's try to look at the truth table for exclusive NOR. So let me get this one off and get, say, exclusive NOR. And for the exclusive NOR, we are still going to maintain the two inputs. For example, we have input A and we have input B. And when input A and input B passes through the exclusive OR gate, let's say we invert, we are getting our inverter here to get Y. So this is the exclusive NOR gate. So now the expression basically would be Y equal to A plus B. This is our exclusive OR. And when we are inverting this one or taking the complement of the output, so now it will now be Y equal to A plus B all bar. So this is what we have. So also from this truth table, we can also extend our truth table here. So let's say, taking the complement of the output, let's say A plus B all bar. So all we have to do here is we just have to look at our inputs here, the outputs here, and we invert, or we take the complement of this output. So when it is 0 here, we have 1. So when it is 1, we have 0, and 1. So also you can also contrast this table here by skipping off this and basically have a rule for this. So how can we get that one? We say we still maintain input A, we have input A and we have input B, and we have input A and this all complement. So this is what you have. You have 0, 0, we have 1, 1, we have 0, 1, 0, 1. So now, since for us to get our output for the XOR gate, we say the output will only be in a very low state when both inputs are the same. So this is just the opposite to that statement. So now when the inputs are the same here, the output will be in a very high state for the exclusive NOR. Like having 0 here, 0, 0, it is 1. And we have 0, 1 is 0, 1, 0 is 0, and 1, 1 is 1. Which is just the same as this. So for our lesson or our lectures for truth tables, this is what you need to learn and understand. So thank you all viewers for listening, and thank you for watching, and your participation will be more needed when it comes to the aspect of asking questions. You can drop your questions in the comment section. Thank you all. And once again, I want to welcome you all to the Eastern Technical University of Sierra Leone. Thank you.